Okay, so last time we saw that people who are moving relative to each other don't agree on simultaneity, they don't agree on the flow of time even. So we're going to see if this time dilation effect is symmetric, so you think the train station clock is slow and the train station people think your clock is slow. We might think we found a hole in the theory, some place where something is broken in the theory, and these things are referred to as paradoxes. There are actually no unresolved paradoxes in special relativity. There are apparent paradoxes that come about because of our attempt to use common sense, which is based on Newtonian physics, instead of relativistic physics, which is how life really operates. So, for the first example, let's say we're looking at this subatomic particle called a muon. This is basically a heavier version of an electron, and you don't see it in ordinary matter. These things are created in the upper atmosphere by cosmic rays, and then they keep moving, flying down to Earth at relativistic speeds. We can create them in the lab, and we find that they have a half-life of about 1.56 microseconds. Notice here this mu for microseconds doesn't have a minus sign superscript, so this is just the metric prefix micro. Anyway, having a half-life of 1.56 microseconds means if you have a bunch of these, after 1.5 seconds, half of them will be gone. They decay into electrons and other things. We wait another 1.56 microseconds, and half of what's left will be gone, so 3/4 of your original amount. It continues like this until they're all gone. Now, one thing to keep in mind is this is a statistical thing. So just like we could say if you flip a coin 1,000 times, we expect you to get about 500 heads. It doesn't work so well on small numbers. If you flip a coin twice, you may very well not get one of each, heads and tails. And that doesn't mean it's an unfair coin. By the same token, if you only have a few muons, you really don't know when the last one will decay. It could be all of them could go in a nanosecond. They could hang on for a year, although that's incredibly unlikely. But it's all a probability thing. So the relativistic thing that we notice is we say these muons are moving very fast, so those clocks are slow. And when we put their speed in for this gamma factor, we say, okay, 1 over square root of 1 minus 0.95 squared, all that gives us a gamma of 3.2. So what that means is we say their clocks are moving at 1 over 3.2 the speed of ours, so about 30% as fast as ours. So that means we expect their half-lives to go from 1.56 microseconds to 3.2 times that, or about 5 microseconds. At the speed they're going, we can just use ordinary Newtonian physics. Newton himself would not know this gamma, so he would say, well, they're going to go, half of them will go in 0.95 c times their half-life, so 450 meters of travel, half of them should disappear. Einstein would say about 3.2 times that, or about 1,400 meters. So the way we do the experiment is to put muon detectors at the top and bottom of a mountain and look at the rate of muons that arrive at each one. And we do this experiment. And by the way, if you want to do something like this, the cost on it is relatively low. All you need to do is find the mountain. It turns out, of course, Einstein is right. So the thing that looks like a paradox is, how do the muons, or a physicist writing along with the muons, how do they explain it? As far as they're concerned, they're at rest, and the Earth is flying up towards them. So how do the muons explain the fact that half of them make it to the bottom of a 1,400 meter tall mountain instead of only making it 440 meters down? The way they explain it is they say the mountains moving towards them are smaller by a factor of gamma. This is called Lorentz contraction. So things in the direction you are traveling, or the length of something in its direction of travel towards you, is contracted by this same factor gamma that we used before. So we say the muons make it to the bottom of the mountain because their clocks are slow, but the muons say it's because the mountain is really very short. So just as you always see the other person's clock moving slower than yours, you always see their meter sticks as being less than 1 meter long.